Example 2.1. A thermodynamic system is taken from an initial state A to another state B and back again to A via state C, as shown by the path ABCA in the PV diagram. A. Rank the temperatures of the three states. Complete the table by filling in either plus or minus or 0 or the sign of the thermodynamic quantity associated with each cycle. Then B, calculate the individual workings of the complete cycle. And then C, draw an energy bar diagram for each process. So what we want to do here is right now, to get a sense of what is going on, we want to rank the temperatures of these three states, A, B, and C. So by looking at the PV diagram, we can immediately mathematically determine the temperature of the rankings. So start with the PV diagram. We can calculate the temperatures. We're not really calculating the temperatures, but it's proportional to that. So if I look at the ideal gas law, it's PV is equal to nRT. If I have a fixed amount of gas, then this is directly proportional to the temperature. But then the temperature is proportional to K micro, which is the same as the internal energy. So let's look at this. So if I look at this thing, I'm going to redraw my PV diagram. So I'm going to go, so here's my PV diagram. And what you're going to see here is that I'm going to call this 1.0, 2.0, and then right here, I'm going to call that 3.0. And so this is the volume in meters cubed. And then up here is the pressure in pascals. Now, if I look at this scale here, I'm going to call this 20, 30, 40. I really don't need 30. So then I'm going to go from state A. And then I'm going to say that this state right here is going to be C. So I'm going to color code these so it's easier to follow. And so what you're seeing here is that this guy's going to go along an isobaric path. Then I'm going to have a blue that goes from B to C. And then I'm going to have an orange path that goes from A to C. Now, if I use the ideal gas law, I could then say, for each of these states, what am I seeing here? So what I see here is that at, let me move this over here a little bit. So if I do that, here's what I see. So if I look at PA, BA, we know that this is equal to, just picking off the numbers, it's, I made a mistake. Look at my A value. My A value is wrong. My A value should be right here. So let me recorrect my graph here. So now it looks like that. So then if I look at my A value, you could see that it's going to be 20 times 1. And this is equal to 20 joules. but that's proportional to the temperature of A. Now, if I do pressure and volume at B, you could see that I'm going to have 20 times 3, so this is 60 joules, but that's proportional to B. And when I go to C, you could see here that the pressure and volume at C is then going to be 40 times 3, which is 120 joules, but that's proportional to that. So when I look at this, what this is really telling me is that I can rank these as TC greater than TB greater than TA. So right away, we've ranked these. And because the internal energy is a measure of the microkinetic energy, an equivalent statement would be that Kc is bigger than Kb, which is bigger than Ka. Okay, so the next thing that we want to do here is that now we want to go in and we want to use this table and we want to fill in the positive and negative signs of the workings, the heatings, and the internal energy. Okay, so what I'm going to do here is that I want to physically understand what is going on. Okay, so here we go. So there's our cycle. So now what I want to do here is that I want to use physical concepts to determine the signs of Q, W, and the change in internal energy. So to do this, so as I start to do this, you want to keep thinking of what causes an increase or decrease in microkinetic energy. Okay, so what I'm going to do here is that I'm going to set up a table to organize these signs. So I've already set it up here. So here's my table right here. So this is the format that I'm going to look at. Okay, so now I'm going to look at the first process from A to B, and you could see that this is an isobaric process. So here we go. So the first one I'm going to go after, then I'm going to go after process A to B, and this is an isobaric, turns out, isobaric cooling / expansion. Okay, so here we go. So what this is really showing here is that this is what I'm seeing. I see that I have the same pressure in a smaller volume and a higher pressure at a bigger volume. Okay, so here we go. So what I'm seeing here is that when I start to look at this guy, I want to keep in that if I have a smaller volume versus a larger volume with the same pressure. So now I'm going to go through the 3 steps here. So the first one that I'm going to do, I'm going to look at this guy, and it says this. So if I look at this thing, here's what I'm seeing. I see that collisions by the gas particles with the piston head cause it to expand, right? There's an expansion. Now, since A micro decreases after a collision, the gas loses energy. In fact, it loses microkinetic energy. So what you're seeing here is that then the work done by the gas is negative. And negative means that it actually lost kinetic energy. So that implies that the work by the gas done from going to A to B is negative. So the gas has to give up energy in order to move the piston. Okay, so now let's go to the second one. The second piece here is that to maintain constant pressure in a larger volume, the kinetic energy at B, the microkinetic energy at B, has to be greater than the microkinetic energy at A, which then says that the change in microkinetic energy is positive. So picture-wise, I imagine this. I have a volume. Here's my piston volume. And what do I know? I know that this has a volume, this has a pressure A, and it has a volume A. So when I look at my graph, I see here that the velocity is that big. So now as I go through my process from A to B, I now increase my volume, but the pressure stays the same. But the volume is definitely bigger. So the only way I can maintain a the same pressure with the bigger volume is that the speed has to be larger. So once again, that tells me that the kinetic energy, the microkinetic energy, or I can also write that as the energy of B, has to be greater than the energy at A. We've already said that, but now we have a picture. So now we were talking about work. The only way to do this is to transfer heat into the gas. So I don't really like my notation anymore. So I'm going to move this over here. And then I'm going to move these guys over here. And do a good job here. And then I'm going to move this right up here. And the only way we can do this here is that if I add heat, right? I have to add heat in order to make it work. So you can see here is that I have heat, and then here I have more heat. And that heat is flowing into the system, right? So it's the only way that I can do that. So then that means here that then because it increases, we could then say that the heat increases K micro. So the heat increases K micro and is positive. So that means then that implies here is that QAB is greater than 0. In other words, there's an increase in heat into the system. So now we've already stated a couple of times here that since the change in K micro is greater than 0, this increases temperature K micro, which is also the internal energy of the gas. So therefore, the change in internal energy is positive. In other words, that tells me here is that the change AB is greater than 0. So if I look at my table, I could then come in, let me see if I still have that. So if I look at my table, here it is, you can now see that this heat has to be positive. The work is negative because the gas lost kinetic energy, and this internal energy is positive as well. Okay, so let's go to the process B here. So when I look at the process B, here's what I'm actually seeing right here. Right, so I'm going to actually come up and I'm going to grab this guy, since I already drew this, and I'm going to keep the process with me. So here's my process right here. So now what I'm going to do is that I'm going to go into the second stage. And this is going to be process B to C. And when we look at that process, I'm going to say here is that this is isochoric heating, but there's no work that's done. And of course, this happens at constant volume. So let's look at this guy right here. So if I look at this guy, here's what I'm seeing. So the first thing that I'll look at is that, so the fact that the volume is fixed. So the volume is fixed. So that means gas particles do not lose kinetic energy when colliding with the piston head. That's what the ideal gas law says. So therefore, Since the gas did not lose, the work is 0. So now I know that the work from B to C is 0. Now we could have looked at that and said it, well, there's no volume change, so then the work is automatically 0. But we want to use physics to understand it. So now let's go to the second piece here. So to increase pressure, and what I mean by that, you can see here is that the pressure of C must be greater than the pressure at B. Since no work is done, heat energy must be added. So if I look at this thing, what am I actually seeing? So I see this volume like this. And then I have a second volume like here. So if I look at this, this is what I'm seeing. Now, if I look at this thing, I know that I have a pressure B here. And I have this volume B. So when I look at this guy, I know that I got to increase pressure. So then the pressure at C has to be bigger than the pressure at B. The only way I can do that is that I have to take my kinetic energy, my speed at B has to be larger at C. Right? So this is clearly B and then this is C here. So then, since I have a higher kinetic energy, what this means here is that in this case, this tells me that if PC is greater than PB, then K micro at C must be greater than the K micro, than B. So what we're seeing here is because the microkinetic energy increased, then that means that the heat is positive. And if it's positive, that tells me that the heat between between BC has to also be greater than 0. Now, even though we've already answered this question, we see here that since the change in K micro, which is the same as the internal energy, is greater than 0, that means it's positive, the internal energy increases. So therefore, we could then write that internal energy is positive. In other words, the internal energy between B and C is positive. So you could see that each of the boxes then tells us where we're at in our cycle. So if I look at this, you could then see here, I could come in and that's positive, well, this is 0 here. Okay, so I'm going to copy this right away because we'll need it again. So now let's go to the process CA. So I'm going to, actually, I want to keep bringing this down with me so that we don't have to keep going back up. So I'm now going to stick this guy right here. And here's our curve right there. So now we're on process C to A. And this is not any process that we know. So in other words, this is not any of the processes we've studied. So what you're seeing here is that this really implies that the pressure, the volume, and the temperature are all changing simultaneously. So here we go. Now let's start looking at this. I'm going to take the exact same process as I did before. So if I look at this thing, here I go. So look at what happens here. So the piston head has decreased in volume. So what you're seeing here, that the gas particles let's see, the gas particles are being worked on by the piston head. That means that the piston head, so this tells me here is that the work of the piston head increases K micro. Okay? It increases K micro after collisions with the piston head. So in other words, the gas gains kinetic energy. So because the gas gains kinetic energy, this work now is positive. So that tells me here is that the work from C to A has to be positive. So now let's keep going along the same process. And then here, the pressure decreases as the volume also decreases. But wait a minute, if the pressure decreases, that implies that there must be less. So that implies here is that we must have less, maybe not say less, let's say there's a decrease in K micro. So what I mean by that is if I go back to the same picture as I've done before, look how we have. We have a larger volume at C. So I have a higher pressure and I have a larger volume at C. And now I have a smaller volume and a lower pressure at A. So the only way, so if the work increases the kinetic energy, what I got to do here is that I got to remove energy from the system, right? So that means here, I need to do some type of cooling in this process right here. So I got to take energy out of the system somehow. So this here is a cold reservoir. So now what you're seeing here is that you're seeing heat being removed. So when I look at my kinetic, my speeds here, this guy has a large speed. This one has a smaller speed. So what you're seeing here, so as I go from C to A here, you're finding here is that the only way this could happen here is that the kinetic energy at C must be greater than the kinetic energy at A, which then tells me that the energy at C is greater than the energy at A, the internal energy. So as our picture says here is that the only way to do this is to transfer energy out of the gas. In other words, there's a decrease in kinetic energy. So that means then heat is negative, which then means that the heating between C and A is now negative. But wait a minute. If the change in K micro has decreased, that implies then that the internal energy, which is the same as micro kinetic energy, the internal energy is negative. In other words, the change in internal energy, which is the same as the change in microkinetic energy, that guy must be negative. So now I could then come in and I can get my graph here or my table. So if I go get my table, it's going to look something like this. So just following my process, by looking at the physics, you could see here that the change in energy is negative, the heat is negative, but the work is positive. So now we have completed this table. Okay, so what I'm going to do now is that I'm going to continue to use that graph that we have over here because I'm going to need it now. So I'm going to stick this graph right over here so that we have access to it right here. So when I look at this thing, I could then say that in summary, I have all my signs, and this tells me here is that here I have to have heat that goes in. Here I have to have heat that goes in, but over here I have to have heat that goes out. B. So we want to calculate the individual workings. And these workings are the work from A to B, the work from B to C, but note we already stated that this guy was 0. So that's not one that we'll calculate. Then we need the work from A to C, and then we need the total work, the net work should be the work from A, B, C, and back to A. So let's go look at these guys. So I'm going to use this curve here and I'm going to modify it. So here we go. So what we're going to be looking at here is that we're going to be looking at the working from A to B. Now, when I look at this working, remember it's the area under the curve. So let me paste this in here. And what I'm going to do here is that I'm going to take all of this heating out because we only want to focus on that. So here we go. So now I'm going to move this guy over here. Okay. So if I look at this guy, what am I actually looking at right here? Well, if I look at the work from A to B, then that means it's the area under the curve. So this area right here is the work AB. So this is the work AB. So I got to compute that. So if I look at the work from A to B, it's the area of that rectangle. And you could see here is that if I have the area of this rectangle, it's got to look something like this, right? So you could see that it has a height of 20. So that's the pressure height between, what is that? I guess, oh, by the way, this is A. So I need the pressure from the difference there and the difference in the volume. So if I look at that, the difference in the pressure is going to be 20 minus 0, which is 20. And then the volume goes from 3 minus 1, which is 2. So this guy is 40 joules. But remember, if I look at my sign up here, note that that work is negative. So I got to come in here by hand and just say, yep, that work is negative. So I now have that working. Now note, there is no working from B to C, it's negative. So now let's look at the working from C to A. So I'm going to grab this guy again. I'm just going to copy and paste it right here. So now let's look at this work here. So note, there is no green work now. It's only the orange work. So if you look at the area underneath the orange line, not only do I have this rectangle, but I also have the area of the triangle. So you can clearly see that this work from C to A is bigger than the work from A to B. So if I look at this, then the work from C to A, that area has to be what? It's definitely the work from A to B, which is this lower piece, plus I got to get this area of this rectangle or triangle, which is then going to be half of the rectangle. So it's going to be 1/2 times the pressure change between CA times the volume change between CA. So if I look at this thing, this is going to be, we already calculated the other one. So it should be 40 and then plus 1/2. So what's the pressure difference here? So if it goes from 40 to 20, so this would be 20, and then the difference between that is 2. So I got 20. I have 40 divided by 2, that's 20. So then this gives me 60 joules. But wait a minute. I look at the work from C to A and it's positive. So I got to come in here and I got to put a positive sign right in here. So when I start to look at these guys, I have that. And then finally, I want to get the working, the network, and the network should be the work from A, B, C, A. So if I look at that work, look what I'm really looking at. So when I look at that work, what picture do I actually see here? Well, for starters here, note that if I look at the green, that green is negative. If I look at the orange, that thing is positive. So I get minus 40 plus 40. So the only area that I'm looking at for the network is the area of the triangle. So in this case here, you're seeing here that the network should be the work from A to B plus the work from C to A, which then gives me 60 minus 40, which then should give me positive 20 joules, assuming that my numbers are correct. So then this is my network. So here's my work from A to B, my work from C to A, and then this is my network right here. So I now have all my networks here. So what I'm going to do now is that the last thing that I want to look at is that I want to look at C here, where I'm going to now draw an energy bar diagram. Most of the time, I just call them bar diagrams. So here we go. So I'm going to color code these things, and I'm going to say that all of my internal energies are going to be blue. So here I go. So the first thing I'm going to do is that I'm going to assume that I have a certain amount of blue energy here. Let me make sure I think this should be okay. So if you look at my cycle, I'm starting at A, and this is the microkinetic energy that I have at point A. Now, as we go from point A to B, if I go get my table, just to make it as clear as possible, we'll use this as a guide. Okay. So I'm going to try to put this over here out of the way. I need to have this out of the way. So here I go. Now, what happens as I go from A to B? Well, what happens here is that I do what? I do negative work and I do positive heat, but because the internal energy changed positively, that means that there's an increase in kinetic energy. So because there's an increase in kinetic energy, I'm going to scale that right now. I'm going to say that it's clear that I increased my internal energy from Ka to Kb. So now I have to sort of like rank these guys. So when I look at my workings, we saw that the work from A to B was negative, but the work from C to A is positive. So let's look at that thing. So I know I have negative work. Let's say that this is my negative work right here. Okay, so this is the work from A to B. So now I got to look at my heat. So the first thing you got to pay attention is that the only thing that's meaningful is the difference between these two guys right here. So this is the change in internal energy from A to B. So now let's see what the heating has to do. The heating is positive, so that means the first thing I got to do is I got to kill off the heat. Okay, so look what I'm going to do now. This little bit is what has to kill off that negative heat. But note that this guy now rises up 2 squares. So then that means I need an additional 2 squares of heating to actually make that. So when I look at this guy, you could see that this is the heating between A and B. So these bars are all matching now. Now look what happens so now I'm at B, and at B, I'm now going to increase my internal energy. So when I look at this thing, I'm going to keep drawing my line here. All I know is that at this point, I have work from B to C, it's 0. So now I'm going to add a little bit of heat. I'm going to say this amount, and this amount of heat is the heating between B and C. And as a consequence, it increases my total energy by 1 square. So you could see here is that this guy, if I add that heat, oops, I put a plus sign here. This has to, I should have put a plus sign right here. And this should be an equal. If I add this red to that blue, you could see here, it's going to be 4 squares high. So then this guy comes all the way up to right here. And this is my microkinetic energy at energy point C. So again, what you're seeing here is that look at this height change. This is the only thing that's meaningful right there, that change in energy. So now what I got to do here is that look at, now I'm going from C to A. Now, if I compare the work, the magnitude of the work at C, CA compared to AB, you could see that the magnitude of CA is larger than the work at AB. So let's, and you could see that it's a factor of 2 to 3. So now what I'm going to do is that I'm going to increase my work now. My work now, according to my sign, you could see that it's positive. So here I go. So I'm going to come in here and I'm going to say that I'm going to do this amount of positive work. So therefore, this is the work of CA. But I have to eject heat. And remember, I have to get back to A. So when I look at this guy, what you're seeing here is that I know the internal energy at A has to be the same size that I started off with. So look at the heating now. So if I look at my heating, what do I have to do? I have to at least kill off the work. Okay, I have to kill off the work. Now look at the height change. This height change, according to this, you could see that the internal energy went down by 3 squares. So then that means, in addition to this, I have to add 3 more squares of heating to make it work. So when I look at this, this is the heating C to A. So there's my bar diagram. So now what I want to do here is that I'm going to move this guy over here. Now I want to interpret what I have. So now, here we go. So now I want to rank the heatings, workings, and internal energies. So here we go. Look at the bigger work. So remember, positive is bigger than negative. So I could see here, just by looking at my picture, the red bar is bigger than the one at BC. So that heat has to be like this. And because QCA is negative, I could then come in here and I could go, here's my rankings for the heatings right here. But just as a reminder, note that this guy is what? This is negative. Now let's rank the workings here. So if I look at the workings, look at the workings. I have a positive work in ACA, and then I have a negative work for AB. So then using signs as we're supposed to, then 0 is bigger than a negative number. So now here's my workings. And again, this guy is 0. And then finally, if I look at my changes in internal energy, the biggest change in internal energy from my graph is A to B, and then look at B to C here. That one's smaller than A to B, and then note that as I go from C to A, that's negative. So then my change in internal energy from A to B is greater than the change in internal energy from B to C, which is then greater than the change in internal energy from C to A. But once again, remember, this guy is negative. What you're going to find here is that, I'm going to just say this in passing here, what you find here is that this is constant pressure cycles usually require more temperature change. Whereas in this case, this is a constant volume heating. Heating usually requires less. And that's a pretty good rule of thumb.